In our previous video, we talked about some general information about the SN2 mechanism of substitution. Now let's take a look at some of the factors that affect the rates of SN2 reactions. So if we look at a general reaction where we have an alkyl bromide and we treat it with iodine to form an alkyl iodide with bromine as the leaving group, we can compare a methyl bromide, a primary alkyl bromide, a secondary alkyl bromide, and a tertiary alkyl bromide. So we're carrying out all of these reactions requiring it to happen by an SN2 mechanism. And for the methyl bromide, if we give this a rate of 1, then the primary alkyl bromide has a relative rate of 0.0061. The secondary is 0.000045, and the tertiary alkyl halide is too small to measure. So even if you really try to force this SN2, it is not going to react. So in SN2 reactions, the reactivity follows the order methyl is more reactive than primary, is more reactive than secondary, is more reactive than tertiary. Why is this the case? For an SN2 mechanism, we know that our nucleophile has to be able to form a new bond with the carbon to push away the bromine. In this case, the iodine has to fight its way past 3 hydrogens. That's going to be pretty easy to do. Here, it has to get past these 2 hydrogens and a methyl group. That's getting harder. Here, it has to reach this carbon. It has to get past a hydrogen and 2 methyl groups. And here, to reach this carbon, it has to get past 3 methyl groups. So there is a lot of steric hindrance. Basically, the groups are bumping into each other. And so the nucleophile can't get past these bulky groups to be able to reach the carbon to carry out the substitution reaction. So for SN2, this is the relative rate of reaction. Let's dig a little deeper into steric effects. We're still looking at the same overall reaction, and this time we are comparing a primary with a primary with a primary with a primary. But what we do have is branching. So here we have 2 carbons, here we have 3 carbons. So adding on an extra carbon, does that make a difference? Adding on a methyl branch, does that make a difference? Adding on 2 methyl branches, does that make a difference? Well, here, the relative rate, if we call this 1, this is 0.8, 0.036, 0.00002. So clearly, what we see here is that steric hindrance is a very, very important factor. The more hindered, the slower the reaction is going to be. Next, let's think about nucleophile effects. So first of all, does the concentration of nucleophile affect the rate of the reaction? Let's say we set up 2 reactions. We have ethyl bromide reacting with potassium iodide, and we repeat the reaction ethyl bromide with twice the concentration of the potassium iodide. Is there going to be a difference? Of course there is. This reaction is going to be faster. Remember, for an SN2 reaction, the rate is equal to a rate constant K times the concentration of the Rx times the concentration of the nucleophile. So if we double the concentration of the nucleophile, we should see a doubling of the rate. So the concentration of the nucleophile absolutely matters. So does the rate of an SN2 reaction depend on the identity of a nucleophile? Here we have similar nucleophiles, except that here we're talking about methoxide, where we have an O- and then the sodium counterion. Here we have neutral methanol, where the hydrogen is covalently connected to the oxygen. And in this case, this reaction is faster. Down here, we are looking at sodium ethoxide. So we have CH3CH2O- compared to sodium acetate. And in this case, this is the faster reaction. Over here, we have the same starting material. We are using ammonia compared to water, and this reaction is faster. And finally, we have ethyl chloride reacting with bromide versus iodide, and this reaction is faster. So clearly, the identity of the nucleophile matters. So we need to think about nucleophilicity, which refers to the strength of the nucleophile. So here we can compare nucleophiles where we're talking about the same nucleophilic atom. In the first example, we have CH3OH. And so this oxygen is our nucleophilic atom. And then in the second example, we have CH3O-. And oh, by the way, we have sodium as a counterion. But this is what we're focusing on. So these are similar, except we're talking about negatively charged versus neutral. And so if you're comparing similar nucleophiles, but negative versus neutral, the negatively charged nucleophile is going to be the stronger nucleophile, which means this reaction is going to be faster. Think about this. Here, this oxygen is willing to share its electrons, but here we already have extra electron density. These electrons are more available, so it's easier to act as a Lewis base, it's easier to act as a nucleophile, and donate electrons. For our next comparison, these are both anions. For the first one, we are looking at CH3, CH2O-, and for the second one, we're looking at CH3, C double bond O, O-. Now, we made comparisons of these when we were talking about acidity. So let's think about that again. Here we have ethanol compared to acetic acid. And we know that this one is the stronger acid. And part of the reason is because of the conjugate base. So with this conjugate base, the negative charge is sitting on the oxygen. There's no opportunity for spreading out that negative charge. Here, we show a negative charge on this oxygen, but we can also draw another resonance contributor where we have a single bond to the top oxygen, double bond to the oxygen on the right. The fact that these electrons are localized on the oxygen, that was bad in terms of stability, but it's good in terms of now reactivity. These electrons are available and are ready to react, and so these can easily attack this carbon, kick out the bromine. Over here, these electrons are delocalized. Sorry, I forgot the negative charge. These electrons are delocalized, and so they're less available to act as a nucleophile and attack here. So this is the stronger base, and that makes it the stronger nucleophile. This one is the weaker base and the weaker nucleophile. So that's why this one is going to be a faster reaction. Keep in mind, earlier in this chapter, we said that leaving group ability is inversely proportional to basicity, but here we're talking about nucleophilicity is directly proportional to basicity. So the stronger base will be the stronger nucleophile. The weaker base will be a weaker nucleophile. Let's continue to compare nucleophiles, but this time we'll be looking at different nucleophilic atoms. So here we are comparing ammonia and water, and we need to decide which one is going to be a better nucleophile. Well, I just said that nucleophilicity is directly proportional to basicity, but another way to say it is that nucleophilicity parallels basicity. So this is true when we are comparing different atoms across the periodic table. So as we're comparing across the periodic table, nucleophilicity parallels basicity. So to figure out which one of these is a better nucleophile, we need to figure out which one of these is the better base. We can look up pKa values, but let's figure this out based on structure. Way back in chapter 2, I believe, we reviewed acids and bases. We talked about how, as we're comparing across the periodic table, acid strength increases as electronegativity increases. So we want to know about water compared to ammonia in terms of basicity. So that means we need to compare their conjugate acids. So we need to compare H3O plus versus NH4 plus, hydronium ion versus ammonium ion. So as we're comparing these acids, oxygen versus nitrogen, we're looking across the periodic table. Oxygen is more electronegative than nitrogen. So this means that hydronium, H3O plus, is going to be the stronger acid. Therefore, ammonium ion is the weaker acid. If H3O plus is the stronger acid, then its conjugate base, water, is the weaker base. And if ammonium ion is the weaker acid, then its conjugate base, ammonia, will be the stronger base. The stronger base is also the stronger nucleophile. And so ammonia is a stronger nucleophile, which means this reaction is going to proceed faster. And in our last comparison, once again, we're looking at different nucleophilic atoms, so bromide versus iodide. And so if we want to compare Br minus versus I minus, again, way back in chapter 2, we saw that when we compare down the periodic table, we focus on size. And so the larger the atom that the hydrogen is connected to, that means that it'll have a weaker bond that's easier to break, and that the conjugate base X minus is going to be more stable. And so HBr compared to HI, HBr is the weaker acid and HI is the stronger acid, which, if this was true, that would mean that I minus would be the weaker base. Yes, that is still true, but that would mean that it's also the weaker nucleophile. Bromide would be the stronger base, stronger nucleophile. But that is not what's observed experimentally. So stronger acid, weaker base, yes, but weaker base does not make it the weaker nucleophile. So it really seemed like when we were talking about acidity, there was always something that had to mess up the rules. And actually, it was the halogens that kind of messed up the rules. Well, guess what? They're messing up the rules again. So we can consider nucleophilicity parallel to basicity when we're comparing different nucleophilic atoms across the periodic table, or as we saw on the previous slide, the same nucleophilic atom but different type of compound. So when we're comparing down the periodic table, there's got to be something different. And the important factor is still to focus on the size. What we need to consider, the first thing, is solvation. So let's say this represents a molecule of water. And actually, rather than comparing Br minus and I minus, I want to go to the extremes and compare F minus and I minus. Okay, so let's say this is F minus and this is I minus. If these are solvated by water molecules, well, the water is going to completely surround the F minus. Whereas since the iodine is so big, the water will solvate it, but it doesn't completely surround it the same way that it does with F minus. So the F minus is kind of buried by solvent, so it makes it very hard for this to shed off all its solvent to be able to act as a nucleophile. Because the I minus is so big and because it's weakly solvated, it's quite easy to shake off a couple of these guys to be able to react as a nucleophile. So because the larger atoms are less solvated, less buried by solvent, they are going to be more reactive as nucleophiles. The other thing to consider, which is still related to the different size, is polarizability. So when we think about F minus compared to I minus, we need to think about these big giant clouds where the electrons are probably going to be. And so keep in mind the orbitals. This is what we're talking about, the region of space where electrons are likely to be. When we have a very small cloud of electrons, then there's not much room for fluctuation. So all of those electrons are probably going to be pretty evenly dispersed. When we have a great big cloud, it's going to be a lot easier for all of the electrons to say, hey, everybody gather over here. And then momentarily, everybody gather over here. And that's going to make this more polar, and therefore it becomes easier to act as a nucleophile. If all those electrons are kind of gathered over here, we've got this extra electron character that can be shared with somebody else. And so the larger the atom, the more polarizable it is. And so as we are comparing down the periodic table, the larger atom will be the better nucleophile because it is more polarizable and because it is less solvated. So for those two reasons, iodine is going to be a better nucleophile than bromide, and so this reaction will occur faster. So to summarize then, in terms of nucleophilicity, if we are comparing the same nucleophilic atom, but our nucleophiles are anionic versus neutral, the anionic species is going to be the stronger nucleophile. Those electrons are more available and ready to react. If we are comparing the same nucleophilic atom, but a different type of compound, then we want to think about basicity, because basicity parallels nucleophilicity. The stronger base will be the stronger nucleophile. If we are looking at different nucleophilic atoms, but we're comparing the same row of the periodic table, so we are going across the periodic table, again, we think about basicity because basicity parallels nucleophilicity. And finally, if we're looking at a different nucleophilic atom, the same column of the periodic table, so now we are comparing down the periodic table. Now we focus on size. So the larger nucleophile is more polarizable and less solvated. So that makes it a better nucleophile. Finally, what solvents should be used for an SN2 reaction? Will solvents have an impact? Well, first of all, we need to think about having something that can dissolve both the relatively nonpolar alkyl iodide and a very polar nucleophile. So we're going to need a solvent that is relatively polar. But there are different types of polar solvents, and we can compare a polar protic solvent versus a polar aprotic solvent. So protic, focus on proton. Does it have an acidic hydrogen? So here, for example, we have water or methanol. These are a couple of examples of polar protic solvents. So we will have our hydroxide and we have our sodium ion. So we want this to be separated away from this so that this can act as a nucleophile. Well, that's great because the sodium ion will be effectively solvated by water, where the partial negative of the oxygen is going to be surrounding the sodium, so that's really great. But unfortunately, the hydrogen part has a partial positive charge, and that will be solvating the hydroxide. And so hydroxide will be very effectively solvated, which means it's kind of buried. And so having a polar protic solvent, you are going to make your nucleophile less reactive. On the other hand, if you have a polar aprotic solvent, so this includes dimethyl formamide, dimethyl sulfoxide, acetonitrile, and many others. So DMF, dimethyl formamide, here we have an aldehyde, but this is an amide, and there are two methyl groups connected to the nitrogen. So oxygen is the most electronegative, so this is going to be pulling electron density away from the carbon, so we're going to have a partial negative. Now, nitrogen will be pulling away electron density from the methyl groups, and so we're going to have a partial plus, but that's going to be really kind of spread out. So polar aprotic solvents have a concentrated negative character so that they can solvate a cation, but they have kind of spread out positive character, which means they're not that good at solvating anions. So if we are still thinking about our sodium cation, this is going to be surrounded by the molecules of DMSO, where the partial negative part of the molecule is going to be attracted to the sodium. But because the partial positive is so dispersed, it's not really going to solvate the nucleophile. And so that makes the nucleophile, not only is the nucleophile not buried, but you have taken away the counter ion. And so that's going to make the nucleophile more available to react. So for SN2 reactions, polar aprotic solvents are definitely best for the reaction. So to summarize SN2 reactions, the substrates will include methyl with a leaving group, such as a methyl halide, primary substrates, and some secondary can undergo SN2 reactions. The rate of the reaction is equal to a rate constant K times the concentration of the substrate times the concentration of the nucleophile. The mechanism itself is concerted, and so both bond breaking and bond forming are happening in one step at the same time. The nucleophile has to add to the backside of the carbon, and this leads to overall inversion of configuration. Sterics have a big impact on SN2 reactions. They are going to be slowed down significantly because of steric hindrance. The nucleophile affects the rate of reaction as well, both the concentration of the nucleophile and the identity of the nucleophile. And then finally, in terms of solvent effects, polar aprotic solvents are preferred for SN2 reactions.